Hello there. Let's do TCP-IP. As we did OSI on the last video, let's do the actual protocol suite and model that you will find on your computers, your routers, and any other device that works at layer 3 or higher. But before we look at the model itself, let's talk a bit about TCP-IP's background, because this is kind of relevant. So TCP-IP evolved from the US Department of Defense DARPA division, a military research agency, and it was originally referred to as the DoD model. And it was used in DARPANet, a military intelligence network that was a precursor to the modern internet. When it became a civilianized technology, if that is a word, we called it TCP-IP because we named it after the two most commonly used protocols in the model, namely TCP and, well, IP you've probably heard about already. So let's have a look at the model. So the model itself has 4 distinctive layers, although depending on whose textbook and definitions you prefer, the names of the layers do vary. But what I've got listed here are the 4 most prevalent or common names associated directly with TCP/IP. Those being the application or process layer at the top, the host-to-host layer below that, and underneath that is the internet layer, and right at the bottom, the network interfacing layer. Now, if you've come across different names, it's very much likely one of those other definitions I spoke about. You can go and check out the Wikipedia page, for example, and you'll see just a couple of the names I've seen for all these layers in TCP/IP. But you know what? It's more about where the protocols are at and how they engage with each other that matters here. So let's get into it. So if we stick OSI, TCP/IP, and something called the equivalent model next to each other, what's quite awesome is that TCP/IP does generally follow the OSI model in terms of what order of operations takes place and how. So as you can see with OSI and TCP/IP on the left and the middle there, you've got OSI's layer 7, layer 6, and layer 5, application, presentation, and session, aligning with the application process layer of TCP/IP. Now what's quite nice about that is when you're sending something, you are going to be doing an application operation, then a presentation, then a session operation before you transit to the next layer. When you're receiving something, it'll be a layer 5, layer 6, layer 7 operation if you're looking at OSI. And then your host-to-host layer aligns directly with the transport layer, which is why with the equivalent model they decided to actually just bring the name transport layer back, because so many people were calling it the TCP transport layer. And then with the internet layer, they brought the network term back because equivalent model, keep it simple. And what I really do appreciate about the equivalent model is they took the network interfacing layer and broke it into the 2 distinctive layers we need, physical and data link. Now the reason why I appreciate that a lot is because if I'm talking about a layer 3 device, like I was a few moments ago, am I talking OSI layer 3, which is the network layer, or TCP/IP layer 3, which is technically, if you count 1, 2, 3, the host-to-host layer? Bit confusing, isn't it? So thankfully, with the equivalent model, which is usually what we use to discuss devices, especially when it comes to the layer they work at, it brings us that OSI layers at the bottom, so that when I say layer 2 or layer 3 or layer 4, we're all on the same page. Yet it still retains the monolithic applications that TCP/IP is known for. Now, let's go check out some of those application services and the protocols and all that good stuff. So here's a little grid of some of the common protocols and services that you will find in the TCP/IP protocol suite. We're not going to go through all of them, at least not right here, mainly because in a later video, we will go through some of the application services at the top there that you need to know for the Network Plus exam. We're definitely going to have a couple of videos about the Internet Protocol IP, and throughout the course, I'm going to be showing you quite a few things, like for instance, when we do switches and how they learn and how the MAC addresses are used and all that good stuff. I'm actually going to introduce you to ARP properly there. So we're not going to dive deep into all of these things, but let's run through top to bottom. So up there at the application layer is where you find the application services that normally the programs that you and I are using on our computer are engaging with to get a particular service. So just giving you a rough idea, Telnet is our original remote administration protocol. It does remote command line. It's quite flexible, very robust, but it's got one big shortcoming, and that is a lack of encryption. But I'll hate on Telnet later. Then we've got FTP, or the File Transfer Protocol, another old member of the family, our original protocol for moving files around. In fact, when the internet was still new, and before the World Wide Web was created that runs on top of it, which is what most of you probably think the internet is, the way we actually used the internet was through FTP. We connected to FTP servers, navigated the directory storage, and either uploaded or downloaded the files that we wanted to deal with. So it was actually more of a file sharing service than actually a web browsing service. Oh, how far have we come? TFTP, or the Trivial File Transfer Protocol. That one deals mainly with ordinary text files and a very simplified transfer system. SNMP, that will definitely pop up later in the course when we start looking at network management. It is the simple network management protocol, which is primarily aimed at monitoring, possibly managing the configuration of your network appliances. It's a nice open standard that's supported by most enterprise networking vendors, so it's pretty flexible there. Then we've got the Post Office Protocol version 3, or POP3, which is a receiving email protocol, usually used to deliver from the recipient mail server to the recipient's client. Speaking of mail, might as well mention SMTP as well, the Simple Mail Transfer Protocol. That is the outgoing or sending email protocol that normally goes from the sender to the sender server, and usually the sender server to the recipient's server. But we'll diagram that out properly when we have a whole lesson or video on application services. Then we've got the ubiquitous HTTP, or Hypertext Transfer Protocol. Lovely protocol, most of you are probably very familiar with it. Although the way the internet's been going lately, you're probably more familiar with its more secure brethren, HTTPS, the one that's using TLS encryption. Thank heavens. Then we've got DNS. Without that, you probably wouldn't be here, because you'd actually need to memorize IP addresses of services on the internet you want to access. DNS, you can just punch in youtube.com, and it'll go and resolve whatever is the appropriate IP address for you to watch this video. Then you got DHCP, or the Dynamic Host Configuration Protocol, a blessing of network technicians everywhere, because it means we don't have to go around manually assigning IP addresses to our client devices. A service in the network can do that for us. And then another very helpful friend, the Network Time Protocol, or NTP, a protocol that just keeps the date and time correct. Gotta love it. Then coming down to the transport layer, we've got two main protocols here, TCP and UDP. I'm actually going to go deeper into them in the coming slides, so don't worry about that too much. But TCP is the more commonly used one. UDP is also used a lot, but you'll see when we get there. Going down to the network layer, the two big kids to talk about is IP version 4 and IP version 6, because that's where our logical addressing, or our IP addresses, come from. And at the moment, a large majority of the world is still using IP version 4. But IPv6 is coming, eventually, like the inevitable heat death of the universe. Anyway, but IP has some supporting protocols, like ICMP, or the Internet Control Messaging Protocol, which is usually used for very, very basic Layer 3 communications. For instance, if you have been sending pings, you've been using ICMP messages to do that. There's another one as well, called IGMP, the Internet Group Messaging Protocol, which is used for multicast communications, which we'll elaborate a bit more on later. But a simple way to understand multicasting for now is it's a one-to-some communication where our target is a select group of people. Then ARP, or the Address Resolution Protocol, very, very helpful fellow, works with IP to associate MAC addresses with IP addresses. We'll play around with that later on when we get to the switches. And then coming down to layer 2, we've got a bit of a weird thing where the standards, and they are more standards really than protocols, kind of extend into the physical layer as well a bit, because they're going to define how we convert the binary to a signal, depending on the network media we're dealing with. But you've got Ethernet, you've got the point-to-point protocol, you've got the point-to-point protocol over Ethernet for when you can't make your mind up. I'm joking, it's not for that. It's mainly for service providers who want to use point-to-point protocol, but the infrastructure that they're connecting to the clients with, or the customers, is more Ethernet-like than serial-like, because PPP works on serial connections, not parallel connections like Ethernet. Then you got frame relay, bit of an old one, but I just wanted to fill the table a bit so it lined up nicely. You get MPLS for the WAN stuff, lovely protocol, that one. And probably what most people know about, which is Wi-Fi, or wireless LAN technologies if you want to be pedantic. And I'll teach you to be pedantic when we do a nice chapter on that later on in another video. But for now, let's move on to talking about TCP and UDP. So TCP, or the Transmission Control Protocol, is one of the namesakes for the TCP-IP model, but it's not alone. It's got a friend called UDP, or the User Datagram Protocol. And let's contrast what makes the two different. TCP is what we call connection-oriented, which means that TCP will establish a pathway over the network and try and keep all traffic for that communication session going through that pathway. It's sort of like if you have a particular route that you like to use to get to and from work every day. Regardless of what happens, you like to use that route. Whether the traffic is good or bad, you like to use it all the time for consistency. That's TCP. Then you get UDP, which is connectionless. UDP doesn't worry about making sure that traffic follows the same pathway. What UDP is going to do is it's going to just make sure that the traffic follows the fastest way, which means that sometimes traffic that got sent later might arrive before the traffic that was sent earlier, because it might find a faster pathway. UDP is kind of like the person that listens to the news and the traffic announcements and whatnot before traveling from home to work or from work back home again. It's that kind of person that tries to always find the fastest way to get somewhere. Now, TCP uses something called sequence numbering as well. What happens with TCP is every bit of data we want to send is going to get an identifying number so that the receiving device can tell, ooh, I'm missing a piece here. Or maybe this piece got corrupted and I'd like it retransmitted. The sequence number allows the recipient to indicate to the sender, can you please resend that piece for me? UDP doesn't do sequence numbering. TCP also does acknowledgements with the sequence numbering. So when I send something as the sender, the recipient through TCP will tell me they're ready for the next piece of data. That's nice. So I know they got it, or I know I need to resend it. With UDP, there's no acknowledgements at all because it depends on sequence numbering. So obviously no sequence number, no acknowledgements. TCP also does retransmissions, where if something doesn't get there, it'll get resent. UDP, on the other hand, no retransmissions. TCP also does something called flow control, where TCP will make sure that it never overwhelms the recipient if it can be avoided. What will happen is during the session setup, the sender will normally say, hey, I can send data this quickly. And the recipient will reply back later in that setup and say, hey, I can work this quickly. And then they'll probably work at the best speed that both sides can manage. That way, the one party doesn't overwhelm the other party. UDP, there's no flow control. But TCP is not completely innocent. TCP does something called windowing, where periodically it'll see if it can maybe send a little bit more data than originally agreed upon. The reason being, maybe I'm doing a TCP session with a server on the internet, and at the time I set up the session with TCP, the server might have been quite busy. But since then, some of the connections and sessions that the server had with other people might have ended, meaning there's a bit more capacity now for me to get my communication over and done with sooner. So TCP's windowing allows me to push my luck a little bit and see if I can get my transmission done sooner. Because the sooner I'm done, the sooner the next person can be done. And rinse and repeat. Whereas UDP, no windowing. Now you might say, geez, why bother with UDP? It doesn't do anything that sounds nice. Well, the thing is, TCP is your reliable but relatively slow protocol, whereas UDP is your fast but unreliable protocol. So UDP is used when we want a fast transport layer protocol. Cool, can work with that. Now let's explore some of these working mechanics. Like I mentioned to you guys how TCP sets up a session, right? A bit of a negotiation between the sender and the receiver. So let me show you what the three-way handshake for TCP session setup looks like. So I'm going to do a flow diagram here between PCA on the left and PCB on the right. So what will happen is PCA will send a message called a synchronization or a SYN message. That is usually the sender saying, hey, I want to send something to you, and these are my capabilities. Are you cool with that? And the recipient will send back something called an acknowledgement SYN. It'll acknowledge, yeah, I got your synchronization message, and I can see what you're capable of, but I want to synchronize back with you, so you know what I'm capable of. And then the original sender sends back an acknowledgement saying, I'm okay with all of that stuff. And during that process, they will figure out what they're capable of from a performance perspective, maybe a bit of security, you never know. But they're going to figure out what each side of the communication session is capable of so that it can work at the best that both can manage. And then we have a TCP session established, up and running. How lovely is that? Now let's talk about those acknowledgements, because they're actually pretty awesome as well. So what happens is a lot of the stuff, there's acknowledgements, the retransmissions, the flow control, the windowing, all of that stuff, relies heavily on the sequence numbers that TCP uses. So think of the sequence numbers like a part number. Part 1 of 12, 2 of 12, 3 of 12, you get the idea. So with TCP, what will happen is I will send sequence number 1, and to indicate to me that they're ready for the next part, the recipient will send me an acknowledgement for the next sequence number. So A sent sequence number 1, B acknowledges it's ready for sequence number 2. So A sends number 2 then. B receives it, B acknowledges I'm ready for number 3. And then sends number 3. That's not so bad, is it? Now what's really cool about the sequence numbers is if, let's say B doesn't get sequence number 3 after a period of time, literally a timeout, or sequence number 3 arrives corrupted, what B will do is it will acknowledge that it's ready for sequence number 3 again. Now, as the sender, A would go, but I already sent you that. So the only reason why you'd acknowledge it again is either it didn't get there and the timeout kicked in, or it arrived corrupted. So let me send it again. That's how the retransmissions work. It's actually pretty elegant. But then we've got the flow control and the windowing. So as I said, the flow control is to make sure that the sender doesn't overwhelm the recipient. So let's say that they agree to initial flow control window size of 1 sequence. In other words, 1 message at a time. So sequence 1, acknowledge I'm ready for 2. Send sequence 2, acknowledge it's ready for 3. Send sequence 3. Okay, cool. Now during that whole process, A might decide, you know what, I'm going to try my luck and I'm going to push the window size up a bit. So I'm going to send sequence number 3, 4, and 5 in one go. Now what's going to happen here is this. If B can handle these 3 sequences, B will acknowledge that they're ready for sequence number 6. Now A knows it can send 3 sequences at a time instead of just 1. B was holding back on A. Either that or a bit of capacity got freed up later on, one of the two. But what if B couldn't handle 3 at once? Maybe B could handle 2 at once. Well, then B would have acknowledged that it's ready for sequence number 5. Cool. That's not too bad either. And to me, one of the most interesting design choices is how the end of the session happens, how the teardown takes place. It's a 4-way exchange, which I think is kind of amazing. I mean, we did this lovely little 3-way exchange so that both sides know what they're capable of. But then we do a 4-way, 1 extra exchange to tear down the session. Wow, this is interesting. So obviously A's been our sender the whole time. So A's now done sending the data and sends the fin or finish message. And B will acknowledge it. But B's not done. B wants to make sure that everything is okay. So B will process all of the sequence, reassemble them, might even pass them up to the application service, holding the session partially open until it's sure that everything's okay. And if everything's fine, B then sends a fin message saying, yep, all's good on my side, and A says, cool, see you later, catch you next time. So that's lovely. TCP is so polite, so friendly, and just gets the job done nicely. What's UDP like? Well, to give you an idea, B can be doing whatever it likes, and with UDP being used as a transport protocol, A will just yell at B to wake up and tell B to keep up with what it's about to send it, because UDP sends as much data as it can as quickly as it can. It doesn't care whether B can keep up or not. B must just do its best. So, which one do we want to use and why? Well, let's work through it. TCP offers us reliability, whereas UDP offers us speed. So with TCP, when all of the content matters and we're not too worried about the transmission time, yeah, we're going to go with TCP. Think of an email. You want the entire thing to arrive. You don't want some of the words to be missing. You don't want parts of the attachment to be corrupted. You get the idea. You want everything to be correct. And while we're at that, you also probably want everything to be in the correct order. The last thing you need is a bad impersonation of Yoda from Star Wars if your email arrives with pieces out of order. But with UDP, its focus is mainly on performance. So when latency and time to transmit matters more than the completeness of the content, that's when we're using UDP. Now, that's not to say UDP doesn't care. UDP is what we generally and favorably call a best effort protocol. It'll try its best, but if it doesn't get the traffic there, it doesn't get the traffic there, and you've got to live with it. Now, something that does make for a great example with UDP would be something like voice over IP. Basically, a phone call using a data network instead of a traditional telephony or cellular network. Now, with voice over IP, you can actually lose a significant amount of the packets that make up the transmission and still have a perfectly intelligible phone call with that person. What will be more beneficial to people is that the phone call over the network, voice over IP, sounds like a normal phone call. It's a natural conversation where I speak, you hear me straight away, and there's little to no delay. But if we try to do TCP with that, where we're trying to guarantee everything being delivered, we're going to get these weird pauses and breaks where I think the person's done talking when actually it's just the protocol freaking out. And that just makes for an awkward and unpleasant conversation. And if you're talking to the right person, like me, the conversation might be a little bit awkward already, and you don't need a protocol making that any worse. So we generally use UDP to make it as real-time as possible and sacrifice on the performance a little bit. In case you're wondering though, the stuff you're hearing right now is probably coming to your computer or your smartphone through a mixture of the two. Streaming services might use UDP just to get the initial content there to give you the impression that there's no loading time, and then use TCP to deliver the content as you need it, as you're watching it, and then improve the quality. That's often why you might notice that the beginning of a video might look quite dreadful, but hey, it's playing. And then within about 10 seconds, maybe 30 seconds, it picks up. Because usually TCP takes over and sorts it all out for you. So yes, we actually do sometimes have services that use a combination of TCP and UDP, which again I think is awesome. However, that's all I wanted to cover with you guys in this video. So yep, TCP is a big thing. And we're going to dig deeper on a lot of those protocols and services as we work through this Network Plus series. But for now, I think that was a good foundation, especially comparing it and putting it alongside OSI and seeing that we generally like to use that equivalent model for TCP/IP so that we got the whole layer 1, layer 2, layer 3 thing going smoothly and consistently. Otherwise, I would like to say thank you for watching. Really appreciate it. And if you've got any friends or family members or colleagues or peers that are interested in networking and Network Plus, don't be afraid to share this video with them. Otherwise though, I'll catch you in the next one.